Yeah, thank you very much, and welcome to the next presentation. Well, before I start, I have to apologize. I think I disappointed a few of our fellow colleagues here because this is the first time that I have already prepared my presentation before. So very sorry. Those who know me from, I don't know, must be 30 years now. Usually I prepared my presentation somewhere in the middle of the night. Okay, we always had a lot of fun. Anyway, so some exciting news about the so-called P4A project, the first geostationary orbiting satellite carrying amateur radio from the state of Qatar. And why Es'hail-2? Actually, this is what you see here is a real drawing of how the satellite will look like. This is a geostationary satellite operated or to be operated. Currently, it is built and prepared for the launch, but this is the Es'hail or Es'hail-2 satellite from the Es'hail satellite company in Qatar. It will be used for direct-to-home TV, for data services, several applications. And Es'hail already has one satellite in orbit, Es'hail-1, but this one is shared with Eutelsat. Eutelsat has 51% of the share, Qatar has 49% of the share, which means the Es'hail-1 satellite is operated, controlled by Eutelsat. And Qatar is basically monitoring, having their service on the half of that satellite, but Es'hail-2 is the first completely 100% by Qatar-owned satellite. And yeah, this is a very interesting story. So first of all, what is phase 4? We have talked already a lot regarding the LEO satellites, MEO orbits, HEO, that was phase 3, phase 3A, B, C, D. Oscar 40 was the last one in the HEO orbit. So so far the last AMSAT phase 3 spacecraft, and we are talking now about geostationary orbit, which means the satellite is basically 36,000 kilometers above the Earth and more or less for the user on the Earth always in the same position. So how did the thing started? Just a short introduction to the timeline. It was basically in December 2012 that the Qatar Amateur Radio Society invited for a so-called International Amateur Radio Festival. It was organized by the QARS, and basically they organized 2 different topics, representative from organizations worldwide, and I was there to represent AMSAT community, in particular AMSAT-DL, so giving introduction about the projects AMSAT has done in the past, especially AMSAT-DL with the high-flying Oscar satellites, even talking about future projects. At that time, we were also working, as you know, on the Mars and Moon missions. So anyhow, then the QARS, the Qatar Amateur Radio Society, and the Es'hail Qatar satellite company made an agreement that we will be able to put or have something on their new spacecraft. So then during the following years, basically up to now, we had a lot of meetings starting from the first ideas, what can we do? Shall we build a dedicated satellite, or should we basically put something on a geostationary satellite? So we looked at various possibilities, starting from a CubeSat, but at the same time I realized, okay, they are going to launch another geostationary satellite anyway, so why not putting something there? Because that would be the first geostationary, and also we were thinking already about some payloads, which would also be the first. So anyway, a lot of conferences, a lot of discussions, a lot of technical meetings actually, because AMSAT is not building the payload. The payload is built by the manufacturer of the complete satellite. So they got basically all the specifications from us. We also provided some sort of technical training because our use case of a transponder is very different to their, usually how they do and operate. So for both sides, it was a very interesting learning curve. So anyway, Es'hail-2 very early announced that they are going to have an amateur payload on their satellite, and they are going really public about this fact. And yeah, earlier this year, basically, we had some final meetings in Japan with Mailco, technical presentations. There were the critical design reviews, so we had to review all the technical parameters from the spacecraft. Does this fit to what we want? But to get it actually working as we hope it will work like. So the last meeting we had basically was in June this year. We had a meeting in Doha, just preparing now the ground segment and talking about how can the user use the spacecraft, what kind of regulations are necessary to keep the usage of the spacecraft in the way where we want to have it. When will it be launched? It will be launched on board the Falcon 9 rocket from SpaceX. There's quite some backlog and some satellites to be launched this year. So the original plan was to be launched by end of 2016. I think that's what we said last year. So officially, the launch is now moved to the first quarter of 2017. So as I said, this is basically a hosted amateur radio payload, what we have here with P4A. It will have an S-band uplink, X-band downlink, a linear transponder. We will see more about it in a few minutes. And the design lifetime is 15 years. So that means once Es'hail is in orbit, which is planned for next year, early next year, at the 26-degree east spot, then if everything goes as we hope it will go, then we have this transponder in orbit for a time frame of roughly 15 years or even more. So 15 years is a design lifetime. Yeah, we are speaking a lot about Es'hail. So what does Es'hail mean? So the story behind the name Es'hail, in English it's Canopus. This is the name of the star which becomes visible in the night sky of the Middle East when the summer turns into autumn. Traditionally, the sighting of Es'hail brings happiness, and it means that winter is coming. Winter means rain is coming. So for them, rain is a good weather. For us, we're all looking for it for the dry season, the summer season, you know. For them, rain is God. So everyone hopes indeed that the naming and that the arrival of Es'hail, that will be good, beneficial for the whole satellite and for the whole amateur radio community as well. And just a side note, when I was in Qatar in 2012, on the day I arrived, it started raining. And it did not rain for almost 2 years. And my hosts already said, wow, this might be a good fortune. So here we are. So this, what you see here now is the Earth coverage, what you can expect. So you see on the rim, down here, Brazil. We have there India. Okay, we see on the next picture a little bit better. It goes up to Thailand. But you can see Europe, Africa is completely in the visibility. So this is another drawing, which is probably better to see what is the Earth coverage. So basically, here we have Thailand, Malaysia, Brazil in the footprint. So it's actually quite a big footprint, what you expect from a geostationary satellite. Down here, we even have some stations in Antarctica. Mikio-san from AMSAT will talk about that later on. We also have a German station. There's actually an AMSAT member down there at the moment. And we are trying to convince them to bring some equipment down there so that they can also operate on Es'hail-2. It's a little bit difficult because yeah, the environment is quite harsh, and if you want to install bigger antennas like dish antennas, usually you need a dome or something to protect from snow and wind and so on. But anyway, they have something like that already there, and let's see what they come up with. Yeah. Other than with commercial satellites, usually we aim to have as much coverage as possible. So the antenna beams on the spacecraft will be that they basically cover the whole visibility of the Earth. You might not be able to read all the fine print, the numbers here on this. What you see here now are some calculations done for different towns, different positions on the Earth. So what will be your azimuth and elevation angle of your antenna? But another interesting thing is, I think those who are installing satellite antenna or TV satellite antennas probably know the skew here. So you will see, I will switch back to the next page. So what you see here, Bochum is easy. Doha is even better, 49-degree elevation of the antenna. Now let's have a look. Yeah, this is an example for Rio de Janeiro. They have 11-degree of elevation. And if you go to Malaysia, to Penang, they have 7 degrees elevation. But when you look here, it's a skew. So when you mount your LNB to the antenna, you must, oops, sorry. So if you can see here, it is very much different. And it is quite extreme, so you would not expect probably, if you haven't installed a satellite TV antenna before, keep in mind you need the skew factor for the LNB. Oops, now I did the same thing we have seen earlier today. Somewhere, okay, I will go down again. So how is the AMSAT payload looking like? So what we see here is a block diagram of our payload. As I said, the whole electronics, the whole hardware is built with space-qualified components by Mitsubishi Electronic in Japan, according to our specification. Actually, so what you see here, for example, so on the left side, basically that is the receiving part. On S-band, right-hand circular polarized antenna. Then we have some filters, some amplifiers, and then we go, in principle, to a module which is called the S-band receiver. There's some filtering, bandwidth filtering done in this module, and then it separates into a wideband part and a narrowband part. So the green part you see here, that is the 250 kilohertz narrowband transponder, which has its own TWT, roughly maximum 100 watt on X-band. Then we have additional bandpass filtering, and then we finally go to the transmit antenna, downlink antenna on the spacecraft. So narrowband is vertical polarized, and if you look here, the wideband transponder, the blue one, goes to his own TWT, and then also into the 10 gigahertz downlink, so into the combined antenna feed. So vertical, the green part is a narrowband, the blue part is a wideband transponder. Even the S-band receivers are 2x2 redundant. So as I said, this is space qualified components. Some of them are basically off the shelf. S-band and X-band is near usually commonly used in the spacecraft business and very near to our frequencies. So they had to do some modifications, but basically they could reuse a lot of components they already use for other purposes. So the narrowband transponder, NB, is a linear transponder for low power narrowband voice, Morse, and digital communication. Preferred modes, basically SSB, CW, PSK, but it's not limited. It's basically everything which is only a few kilohertz of bandwidth is fine for us. We have a total of 250 kilohertz allocated bandwidth. It's a non-inverting bandpipe transponder. And if we assume SSB, we can have roughly 50 simultaneous two-way carriers to serve about 100 users at a time. Distributed probably then over 24 hours, 7 days, and so on and so on. It's continuously there. So the X-band downlink, basically you can use a satellite TV dish for that. Yeah, you see a few numbers. So in areas, let's say Europe, Middle Africa, a 75 centimeter dish will be easy. Actually, this was a mistake. A 60 centimeter dish will be around the coverage peak, so that means more or less in the antenna on the spacecraft has some shaping factor, but basically Africa, Europe, even a 60 centimeter dish should be fine. Then we come more to the arrow of that. This will be 75, and 90 centimeter dish is really the worst case. It means you are in a rainy area at the end of the coverage region like Brazil and Thailand. So under normal circumstances, say from Rio, you can use a 90 centimeter dish on the downlink to receive the signals from the narrowband transponder. As I said before, our downlink on the spacecraft on X-band is linear polarized. It is vertical for the narrowband transponder. The uplink on S-band is right-hand circular polarization. And yeah, for normal SSB QSO, you will need about 5 to 10 watt PEP, assuming you have a 75 centimeter dish antenna. So what will be on the narrowband transponder regarding band planning? At the moment, it's not fixed. We are discussing some ideas. Should we have some kind of band plan, or shouldn't we? It's not clear. But what is clear, we will have some beacons at both ends. These beacons will be generated on the ground. We come back to that later. We may decide to have an area, probably not 30%, for some CW modes, mixed modes, and SSB, and maybe additional. But maybe even with AMSAT-UK, maybe we should discuss this internally if there's a need to or not. I'm not really sure. I know we had on Oscar 10, we had the band plan like this. Actually, this was coming from Oscar 10 and Oscar 13 timeframes. I think on Oscar 40, we already said, let the users sort that out by themselves. Not sure how this will work here. What is important for us, in some way, we need probably some sort of self-regulation, because we want to keep Es'hail-2 happy about the kind of usage of the satellite, and not that we end up in a kind of chaotic way, because we really don't know when the spacecraft is up how many users will be there. We tried to make some calculations, but it's very difficult. In theory, it can be a lot. In practice, it can still be a lot. Because it will be, as you later hear from Achim, it will be kind of easy satellite. So the wideband transponder, this transponder is, as the word wideband already says, it will be used for wideband transmission, wideband communication. So the first thing you think about is this DATV, digital amateur television, with the DVB standard, but even high-speed data transmissions are possible. And this was also one good selling point for Qatar. So this is not only the first amateur radio transponder in geostationary orbit, this will also be the first DATV transponder in space. Remember, the DATV on the ISS is a downlink only, it's not a transponder. So this would be the first digital amateur television transponder in space. The bandwidth of the wideband transponder is 8 megahertz. Yeah, depending which symbol rates you use, which coding, if you use DVB-S or DVB-S2, there is room for several signals, as we will see later. We can provide HD quality signals actually, or several standard definition picture quality signals. So we also have a lot of varieties there. Anyway, it will be a little bit more difficult to transmit, but receiving will be very easy. So if we look on the downlink, X-band downlink, basically you can use the same dish you will use for the narrowband, which means a 60 centimeter dish will easily work in the coverage peak. A 75 centimeter dish will be basically the average, and again at the end of the coverage region, a 90 centimeter dish will be required. So with a 90 centimeter dish and LNB, you will already be able to receive the DATV signals we are going to transmit. Uplink, again, S-band right-hand circular polarization. And if we, for the uplink, we are assuming more or less 100 watt PEP into 2.4 meter dish. So the DATV uplink for the transponder is nothing you can do with simple equipment. 2.4 meter dish is probably already not so easy for everyone to install, but for mobile operations maybe, or something, or if you have a big garden or a big roof, it will be fine. But so we think this transponder will definitely see a lot of uplink stations, not so many as a narrowband, and we believe the majority of users will be more in the receiving only style. So it depends very much what are we going, how do we attract the people, what kind of signals will we send up to the spacecraft. So we are planning to have a so-called beacon, a DVB-S2 beacon from Qatar, which will provide perhaps some live webcam images and even some promotional videos about amateur radio activities. But we will see later on there are also a lot of other interesting possibilities. So a short overview about the target user station. So for a setup for SSB communication, receiver antenna 60 to 90 centimeter satellite dish, a receiver, LNB, probably a DVB-T dongle, software-defined radio. There are a lot of possibilities. And the transmitter, as I said, for SSB, 10 watt PEP into a 60 to 90 centimeter dish, and most likely with an up converter from 2 meter, for example. And for the receiver, you would also perhaps down convert to 70 centimeter. There is already some hardware in development. Some of the known providers of converters, transverters already prepare for this. So we will see this also later in Achim's presentation. This is an overview again regarding the frequencies. So here you see the uplink. So here we have the narrowband transponder uplink, and here the wideband transponder uplink. As I say, both are right-hand circular. So on the spacecraft, they use the same antenna. For the downlink, we have here the narrowband and the wideband. The wideband 8 megahertz wide, the narrowband 250 kilohertz wide, and we have them also separated by the polarization. We have a leaflet. You find it in the AMSAT-UK office in the room outside. We have the leaflet with all the information. So take as much as you want. So what is the status about Es'hail? As I said before, all the critical design reviews are already passed, and they have already built the flight hardware. The spacecraft is now undergoing final testing, which means thermal vacuum testing, vibration, all the usual environmental testing you do with such a spacecraft. And this is here the real spacecraft. The panels are not mounted here, but this is basically the real spacecraft you see here from a meeting which was in June 2016, only just a little bit over a month ago at the Kamakura factory of Mailco Mitsubishi Electronic Company. So the satellite is in very good shape. We are waiting that it is being finalized and shipped to the launch site in the US. Meanwhile, and that was one reason for the meeting we had this summer in Qatar, was to prepare the satellite control center for Es'hail-2. So Es'hail, a little bit outside. So here you see the main city, town of Qatar. And somewhere, I will not just show where it is, somewhere here in the desert, there is currently a big control center being built. The whole Es'hail satellite fleet, and they are planning, I think, at the end, perhaps 6 satellites. They have some very big plans for the next future. So all the satellites will be controlled from there. They will also provide similar services to other satellite companies. So from there, they uplink the DTV, direct-to-home television signals, data, internet, whatever, directly to the spacecraft. And here you see a small antenna farm dedicated to our satellite. And this is Mr. Saban from the Secretary of QRS. And as you can see here, we have a dedicated 2.4 meter antenna already. This antenna, it's already in place and basically working. So they are preparing to have everything ready for the launch as well. And in this satellite control center, called SCC, this will also be the location of the AMSAT transponder ground segment. So what is a ground segment? The ground segment in this case will be our LEILA-2 system. Keep in mind, the transponder is only a bent pipe transponder. There is no computer, nothing else in the spacecraft which controls or which has control over the usage of the transponder. Even there is no beacon, no telemetry coming out of our transponder. Indeed, the spacecraft itself, they have telemetry beacons, everything, but our payload does not have any telemetry transmitter or beacon as we know it from our previous spacecraft. So in some way we need to have a little bit control, and one idea was that we built this LEILA system, which you probably know from Oscar 40. If there's the problem with such linear transponders is with so-called uncoordinated access, we don't have direct control over the user. If a user is using way too much uplink power, too much excess power, you know, from normal linear satellites, the AGC in the receiver of the transponder goes up, and all the other stations which are using little power basically fall out of the transponder. They get weak, or you can't hear them because one station is using too much power, and you know this from the linear transponders. And so for Oscar 40, we built the LEILA to accommodate this and to have some sort of control. But here we will have it on the ground. As I said, there is no intelligent electronic in our module. So we are going to build a ground station. We are just preparing for that. We already have the 2.4 meter dish installed. It is also for the X-band downlink. We will do the in-orbit verification and monitoring from there, and we will operate the LEILA, which will analyze the passband and send back marker tones to the station which is using too much uplink power. Also, we will generate pseudo beacons, the general beacon and the engineering beacon at both ends of the transponder, as you know it from the previous phase 3 satellites, so very similar with 400 bit per second telemetry. So we are going to build a ham radio shack down there. So the basic idea is when there is the official inauguration of the satellite, of our transponder, some high-level state people will probably press the button and officially open the transponder. And I should have mentioned before, that was one of the pictures on the first pages, the former vice president, no, former, yeah, what do we call it, vice president? Deputy, yes, deputy prime minister of Qatar is a radio amateur, and he is also the president of the QARS. So sometimes you must have the right people at the right positions. So, as I said, we will have the Radio Shack there. We will also install the DVB as equipment for the DATV beacon. We will have the LEILA system there. We also plan a backup station at the QRS club station and also in Bochum near our 20-meter dish. Yeah, this is a block diagram about the ground station segment we will be having in Qatar. So here we have our downlink, so the receiving part. It will go through some splitters to the LEILA system, also go through to the LU band down converter. So we go down with U band into the Radio Shack where we have our transmitter and receiver to operate the spacecraft. LEILA-2 will indeed go to the uplink again. And also we have here a V-band to L-band up converter for the radio from the Radio Shack. So the upper part of this picture is the shelter. The lower part is the Radio Shack, which is even physically in a different location. So the shelter is basically, this is what we call a shelter. So this little building. So in this little building we have the up and down converters. Their internal intermediate frequencies, everything is on L-band. And from there we have probably a very long cable to the main building where the Radio Shack will be installed. In the Radio Shack, we have a satellite receiver, basically to monitor our own transmitted signal or look at other signals. We have a VHF, UHF transceiver, so that we can even do SSB contacts from there. We will have the DATV modulator, for example, video camera or any kind of media can be played from there. Actually, even one of our contact persons in Es'hail-2, he is looking to make his ham radio license, so he may even by himself operate the club station there. Yeah, so pseudo beacon. Why pseudo beacon? Pseudo beacon because the beacon is generated on the ground and not on the spacecraft. So we generate a beacon on the ground, send it to the transponder, and it comes down. So the user does not see, it's not generated on the spacecraft, it's actually generated on the ground. And the reason is actually so that the user is basically able to adjust his transmit level to the same level of the beacon. As you know from the phase 3 satellites, it was always like that. Your signal should not be stronger than the beacon. So you need a reference signal. If we don't have a beacon or nothing here, you don't know, am I too strong or is my signal weaker than the average? So the pseudo beacon will help the user to adjust his own uplink signal. And another idea is we will have this old style, not old style, it was quite sophisticated, the 400 bit per second BPSK telemetry with forward error correction, which we used on phase 3D, Oscar 40. And we will be able even even I said before, we have no telemetry directly from our transponder, but we will get it through the SCC, so the main satellite indeed is having telemetry channels, and they will extract some telemetry channels which will be interesting for the amateur radio community. Output, power, temperature, things like that, which someone even might use for educational purposes, want us to transmit. So it has several interesting effects, but the main reason is indeed to mark the end of the passband on both sides, and also for the user to have a reference level. Okay, I have to speed up, because I have still a lot of foils. So 5 minutes, you need to give me more. But you know, always like 30 years, always the same thing. And you know. Okay, LEILA and OSCAR 40. We already had the LEILA of OSCAR 40. LEILA is a German acronym for Leistungslimitanzeige, which means power level indicator. It was the original LEILA concept was designed on OSCAR 40 by Karl Mainzer, Dr. Karl Mainzer DJ for ZC, and Matthias Wittmar S53MV from Slovenia. So these both fellows, these really cool people, they designed the LEILA concept for OSCAR 40. It was a hybrid, mostly analog design. It was able to, as I said, to have a tunable notch filter, to have a jam signal source, a kind of siren. Because this was in the spacecraft itself, notching was easy. With a ground-based LEILA, we cannot use a notch because of the time delay. But we will have the jamming signal source again. Then Howard Long for phase 3E, he was thinking about a completely digital design. So Howard called it Stellar, you might remember. So this was part of a software-defined transponder, which would also have this LEILA capability, but in the spacecraft. So LEILA-2, we call it LEILA-2. By the way, LEILA is a very well-known name in the Arabic region. So Es'hail-2 was very delighted when we started talking about LEILA. Oh, LEILA. And so they like it, and so we kept the name, and we just name it LEILA-2. So LEILA, as I said, LEILA-2 is ground-based. There is no notch filter, but there will be this siren. The siren will look for, if someone in the passband is stronger than the beacon, the LEILA will put a marker on it and generate some kind of do-do-do-do-do-do signal, so you know I have to decrease my power. This was one interesting learning point even for Es'hail and for Melco. For them it's very easy. On their satellite transponders, they just take the telephone, call the uplink station and tell them, hey, Al Jazeera, you have too much power, please reduce your uplink power a little bit by 3 dB. They had to understand that amateur radio, this does not work. We don't know your phone number. We cannot phone you and tell you, so we need LEILA. Actually, what you see on the table, but I think Achim will talk about it later on, is already the prototype hardware of the ground-based LEILA system based on the red pitaya. So I make it quicker. Maybe, Achim, I don't know if you can talk a little bit more over that later on. Anyway, we have the slides. The Radio Shack. Yeah, this is an overview of the Radio Shack in the Spacecraft Control Center in Doha. We will have here the DVB equipment for the up and downlink. We will have here the Kenwood TS2000E, which was kindly donated by Kenwood. And all this equipment will be in the Radio Shack in Qatar for demonstration, but also for generating the DVB beacon and the LEILA system. Okay, I make it a little bit quicker. This is some of the DVB S2 hardware which is already available and which basically we will use here in Qatar, in Bochum, and possibly other stations to uplink signals. This is a downlink system. It's available, well, from SR Systems, but this is a radio amateur, also an AMSAT, long-time AMSAT member. He is developing all this DVB hardware. So Okay, I had here a few more slides because we were talking about DVB, DVB-S2 and DVB-S standards. At least for the downlink beacon, we will promote DVB-S2. Why? DVB-S2 has roughly a 2.5 dB better gain or better performance compared with DVB-S. It also is, we have some interesting features coming with it. Okay, would be the time for the time we have would be too short, but DVB-S2 already comes very close to the Shannon limit, so you can't make it better. Also, it is more spectral efficient, and what is very interesting, they have, even compared to DVB-S, a better shaping factor. The shaping factor, basically, when you have your spectrum, DVB-S2 signals by the used modulation and standards have from the bandwidth much more efficient. So another interesting fact is DVB-S2 has a pilot tone, so synchronization of the downlink signal is much faster compared to normal DVB-S. That will be also one reason why the ISS will soon switch to DVB-S2 when they have the hardware brought up. There are some other technical changes. I think I go too much into detail, but in general, DVB-S2 is much more efficient. That is actually the reason why everyone is even commercially using DVB-S2. An interesting part of it is DVB-S2, unlike with DVB-S, is having a so-called BB frame, baseband frames, and these are time multiplexed even in the physical layer. So you can have different kind of input streams. This can be a video signal, it can be digital data, it can be whatever, and these frames will be integrated into one signal. So one possibility is we can have on the same frequencies, the same signal, we can have a high definition signal with a much higher coding rate, with whatever modulation, but high definition. But we can have on the same, for example, the red would be the high definition and the blue one could be the standard, the low definition signal with a very low coding, very high coding and low symbol rate. So you see the same signal, you have a very small dish, maybe you want to try with a 45 centimeter dish, you can still receive the lower quality signal, you might not see the high definition signal. So there's a lot of room for experimentation. We are even thinking about from certain times to switch from DVB-S2 to DVB-S format, because at the moment the majority is using DVB-S, but then they can see what is the difference between both standards. We have created a kind of draft band plan for DATV, but this is not fixed. We are still in discussion. We actually, the BRTC, and we are going to have a meeting tonight and discuss various proposals. How could a band plan for DATV look like? But something we came up is we will have here our beacon. We call it beacon because this will be more or less permanently operating, transmitting some either stand images or a propaganda video about amateur radio, a webcam, or a live event from somewhere. When there's, for example, we hope the next AMSAT-UK Colloquium, this will be the live stream from here. And there will be indeed room for the users. One interesting thing we also planning, we even plan a kind of command uplink because Doha is far away from Germany, from our team. If we want to have a software update, it's not so easy because like if you work on a big company, you have a lot of security issues. So normally they won't let you go into the intranet and have access from outside and so on. So as I said before, DVB-S2 is also able to have digital data. So we will have actually an Ethernet connection. We will be able to switch the system into a kind of Ethernet mode. So then, for example, in Bochum, we will have here a kind of command uplink, and we will be able directly via Ethernet to go into our computer, update software, update media files, put a new video on there, and we will have a lot of possibilities. Even some possibilities we have not yet thought about. So it's for all very exciting and new technology. Okay, here we will have later on today, we will hear from David and Noel a little bit more about it. And that's where the BATC also comes into the business. How do we coordinate all this traffic on this digital transponder? I mean, on the narrowband transponder, we have our LEILA system, but how do we do this on the digital DATV transponder? Another level of complexity is you have so many different modes available, coding rates, modulation rates, symbol rates. So whatever, if every user is using a different parameter set, the others will not see it by default. You need to know what is a symbol rate, what is a coding rate. Then you have to actually configure your receiver to the same settings before you will receive before you even will see an image. So it's not like SSB where you tune, oh, I can hear you, more complicated. So a kind of real-time coordination is needed, and that is where BATC is working on. I will show this only for a moment, for a few seconds. They are thinking about creating a web-based SDR server where you see the spectrum from the DATV signals, a chat room, and then, for example, if somebody is going to transmit, he can say, okay, I'm on this frequency here. I'm using these and these parameters so that everyone else can tune on the frequency and easily look on his signal. So equipment for DATV, the probably cheapest way is to go to a supermarket and buy one of those cheap DVB, off-the-shelf DVB S2 receivers. They are already capable of DVB S2. And they basically work out of the box. So what else do you need? You need to, basically, you will need a modified LNB because the television satellites don't work on amateur frequencies and vice versa. So we need some modified LNBs so that we can tune in on the amateur radio frequencies.
I've got to ask you to finish.
I'm almost done. Partners, so Es'hail-2 satellite company from Qatar, indeed with support from the government, with the order from the government probably. AMSAT-DL QAS indeed is a big player here. Then we have JAMSAT, even Japan is far away and they are not seeing the spacecraft. They are putting a lot of the efforts in developing equipment for the user. So we will see a lot of interesting concepts coming from Japan. Also JAMSAT helped with Kenwood, donating one of the transceivers. We bought even 3 more. They didn't donate, but gave us a good price. AMSAT-UK indeed for support with BATC. We have AMSAT-UH involved. Michael Fletcher, OH2 AUE. He has some quite good knowledge about commercial TWTs and the commercial satellite business. So he was very helpful when we did the specifications. Even the commercial industry is using different terms than we are using, so this was a good learning curve for both sides. And then we have these guys developing the DVB, Groundstation stuff in Doha and Bochum. So conclusion, that is the last page. Es'hail-2, QRS and AMSAT-DL are working towards the first linear ham radio transponder in geostationary orbit, P4A. Launch is planned for the first quarter of 2017 with SpaceX Falcon 9 launcher. We will have 2 transponders, a 250 kHz narrowband and an 8 MHz wideband transponder. The target antenna size for receive and transmit for narrowband is in the order of 60 to 90 centimeter antenna dish, which is not really huge. The only exception is the uplink for the wideband transponder. So if you want to send a DATV signal, you need roughly a 2.4 meter dish and 100 watt of power. As I said, in the office of AMSAT-UK, we will have a leaflet where you can find all the frequency, all the details again, and you will also find it on our webpage. So thank you very much. And now I wish you a lot of fun with Achim's lecture. Achim will talk now about the user equipment for the narrowband transponder. And then our colleagues from BATC after this will talk about user equipment for the wideband transponder. Thank you very much.
Thank you. Ask Achim to follow on directly and save the questions until the end of this session, because I suspect some of your questions might be answered by Achim and Miko as they go through their things. As a matter of interest, while we got a break, how many people are watching the TV stream at the moment? Do we know? How many people watching at the moment? Do we know? Have we got any idea? 110. Okay. Wonder if we'll get more this time next year via the satellite. We'll have to see, won't we?
We can't count them anymore.
Pardon?
You
Can't count them. No, that's interesting. Achim really needs not much introduction. He's one of the leading lights in AMSAT-DL, although he actually comes from Switzerland.
No, I don't. I live in Switzerland.
Oh, you live in Switzerland? I'm sorry. Well, he's deserted then. And is one of the brain boxes. It's one of the reasons we don't have a quiz any longer at the AMSAT-UK colloquium, because AMSAT-DL always won it. So there we go. Anyway, over to Achim.
Thanks a lot, Jim. So thanks, Peter, for using 20 minutes of my 40 minutes allocated. So I think I have to speed up quite considerably. So first of all, you asked me to say a bit about the LEILA 2 system. So I'll hold it up briefly. You can later have a short look, maybe after the talk. So it's basically a breadboard model of what Howard Long, G6, LVB, and myself have envisaged for being used on the ground station. The Red Pitaya is basically a Linux computer outfitted with some very powerful ADCs and DACs, so it can basically directly process the baseband of the transponder as it comes down from the satellite. And something like 250 kilohertz of bandwidth for nowadays DSPs is really not so much of an issue. Putting this on the ground doesn't make a problem in terms of power consumption or radiation testing or whatsoever. If it breaks, you switch on the secondary system, so not really a problem. For those who are interested, it's running right now a demo. And yes, the 400-bit PSK beacon should run somewhere on 145.795-ish. And if you tune down a bit, there should be another CW beacon, actually. I changed the code. If I called the right one. Try to find it. It can be a couple of kilohertz. Okay, I'll just continue. You will notify when it's coming up. We have identified a couple of issues with the prototypes. Actually, these are 0.1 versions, and we're quite happy that they work at all. And probably the next version will be already the final one. Okay, so going to the ground stations. I had a bit of a hard time deciding on what to talk about, because I mean everybody of us knows about user ground stations. And it would be rather easy just tell you, I mean, you need so many watts and that antenna, and that'll be it. But actually, Twitter is very powerful. So I twittered a couple of days ago, what would you like to hear in this talk? And then we came up with stuff like this here, some microwave specialties and some antenna theory, because I would expect that most of you are familiar with CubeSat operations, VHF, UHF operations. And except for the experts from BATC, we are not so much into using microwave antennas. That is mostly parabolic dishes. So I will expand a bit on that. Briefly recite the transponder data as we have seen it already, and then give you some hints about what we have been planning for using the S-band uplink and the X-band downlink. So very generic ground station building blocks are something like that. So we have a transceiver, an up converter, because usually the transceiver doesn't work in S-band directly. We need a bit of extra boost for the signal and a transmit antenna, and for the receive side, basically the whole thing inverted. And that is a kind of very generic thing. Normally what we do have is something like a full duplex transceiver. We still advertise using full duplex to monitor your own signal, especially when LEILA kicks in and tells you to reduce your power. The receive side will be merged to something called a low noise block. We'll come to this in a minute. The antenna, if you want to do it very elegantly, you want to go for a dual band antenna. And I won't talk about the transceiver because that is certainly something which is off the shelf. And I would assume that if not already present, you can use virtually any transceiver which fits your needs in terms of intermediate frequency at that level here. So we will go, first of all, to some microwave specialties. What we already know from VHF and UHF is that we do have quasi-optic radio propagation. So to some extent, VHF and UHF can bend around, let's say, walls and houses, but it's not very efficient on 2.4 and more so on 10 gigahertz. It's an absolute no-go. So even if you have a tree in your line of sight, you better take out the chainsaw. Antennas are very much like optical systems. Again, we know from VHF and UHF, you have these Yagis, you have the elks, you have the arrows. They don't look like a real optical system, do they? But then again, if you look at, for instance, the 10 gigahertz antenna David Bowman has put in the AMSAT UK room, it looks like kind of parabolic concentrator, and this kind of resembles like a telescope. And these parabolic dishes, I mean, they really work like reflector concentrators. So the antennas are quite well understood. For the S-band uplink, we can harvest a lot from the Wi-Fi/ISM industrial, scientific, and medical band components. They are very, very widespread. They're going to be, or they are very cheap and getting even cheaper on the X-band downlink, especially if we are so close to the direct-to-home segment, which starts at 10.7 gigahertz. We can harvest a lot of components, performance, knowledge, experience. And I strongly believe we should use these assets to its best because we don't have to reinvent the wheel once more. So starting with the receive side, it's all about noise actually. If you're talking about signal to noise, then half of it is noise, and there's a very popular plot or chart of the noisy sky. And actually, if you try to look for this chart, the first hit from Google, which will pop up, is from Phil Kahn, KA9Q. But he was so kind to point us in the right direction where the original chart comes from. It's a NASA publication. And what you actually see here is the frequency in gigahertz on the x-axis, and the y-axis is the sky temperature in degrees Kelvin, and it's a log-log scale. So VHF somewhere here. So the sky temperature is already around something like 100 to 350, 400 kelvins. This is a so-called non-thermal background, so that's basically electrons in the galaxy spiraling around some magnetic fields and emitting kind of radiation. So this is a kind of natural limit. It kind of levels out at 1 point something gigahertz. You have here the hydrogen line at 1.42 gigahertz. And beyond, let's say, 50, 60, 70 gigahertz, you end up with a quantum limit. That's just basically quantum mechanics. And the flat floor is determined by this famous cosmic microwave background, this 2.7 Kelvin. Unfortunately, that's not the whole story. We have an atmosphere. Well, not unfortunately, it's quite nice actually. But in terms of radio propagation, it's very unfortunate because it adds a bit of, let's say, extra temperature here in the what we call radio window. So we're basically from 2.7 Kelvin up to something in the order of 5 to 10 kelvins. We have a water absorption line around 26 gigahertz, and oxygen absorption line are around, I think it's 20, 30, 40, 50 gigahertz something. But still, it's very obvious that the region between 1 and 10 gigahertz is very fortunate in terms of radio propagation. Now keep in mind this sky temperature, which is in the order of 10 kelvins. So as soon as we try to calculate our system noise, we basically have to factorize in all the different components. So the complete system noise is basically receiver noise plus the noise coming from the antenna. And then the antenna noise is noise from the sky pointing upwards, and some ground losses like bad connectors and things. And losses, sorry, the connectors are the losses before the receiver, and the ground losses are basically the parts of the antenna which do not look up to the sky, but maybe look down to the ground. And the ground is fairly warm, it's 300 kelvins. And the receiver noise is mostly the noise of the first amplifier stage, which we see here. I didn't know the name of the formula, it's from a guy called Fries. But actually what it says that the noise contribution, the total noise contribution here, is dominated by the noise of the first amplifier stage. So basically this is a formula of noise if you have cascaded amplifiers. You have first stage amplifier, second stage, third stage. What is really interesting now is, here's the temperature of the first stage, and the gain of the first stage is affecting basically the temperature contribution of the second stage, right? So whatever temperature the second stage has is reduced by the gain of the first stage. And the only stage which is unaffected is the first stage itself. So here is a term which is completely unaffected by any gains, and therefore the temperature, the system temperature, or the noise temperature of the first stage is the real critical issue. And that's why we always say you have to place the LNA as close to the antenna as possible. That is mostly critical at the higher frequencies, namely at 10 gigahertz. So what can we actually achieve at 10? So the LNA noise figure is at the order of 0.7 dBs. If you go on eBay, Amazon, you will find LNBs with a quoted noise figure of 0.1 dBs. This is rubbish. The FETs, the transistors itself, can manage on paper something like 0.4 to 0.3 maybe. But then you have the PCB, you have the connectors, you have additional losses, and at the end of the day you will end up with 0.7-ish. That's 50 Kelvin. So if you add up now this Fries formula and put all the stages back together, something like 120 is certainly possible. The antenna noise temperature, I say now less than 100. We have seen in the diagram the optimum would be something like 10, but it would basically pointing up and you don't have any atmosphere above you. So you have to factorize in a bit of bad weather, maybe a small tree which you're not allowed to chop off. So 100 Kelvin is reasonable. So if you add now the total receiver noise with the antenna noise, it's in the order of 220 Kelvin, which is quite realistic. So coming now to the real deal. Dual band antenna. Coming to the antenna, or some theory basics of the antenna, that is basically the formula for antenna design, which is really important, which basically gives you the gain in dBIs of any antenna given the aperture, so that's the area of the antenna, the wavelength of the frequency in use, and the efficiency, eta. So wavelength is easy, so that's either 10 gigahertz, let's say 3 centimeters, or 13 centimeters for 2.4. The area is just radius squared times pi, and the efficiency is something we can influence. Typically between 0.5 and 0.7. I have to say for the amateur radio people, probably more like 0.5. If you can spend a lot of money and do some beam shaping, maybe you will be able to reach 0.7. But it only makes 1.4 dBs of a difference. However, doubling the diameter of your antenna makes 6 dB of difference. That's 1S level. And typical numbers for 60 centimeters are here. 21 dBs on S-band, 33 on X-band. That is what you can, well, safely expect. And you can scale these numbers by any diameter you want to install, or you are allowed to install it by your XYL. So, if we stick now to the parabolic dishes, the shape is more or less a given thing, except for one parameter we'll come to in a minute. But what one should not neglect is the dish feed, because somehow we have to get the energy into the dish if you want to transmit, or you have to kind of collect the energy which is reflected or concentrated by the dish into a feed. So in the past we have seen many approaches, and all of these are kind of valid for different applications. We have dipoles, patches, horn, helixes, and the dish is actually only the focusing element, the real antenna which converts the radio wave into something which is an electric signal. That's the feed. And in the perfect of all worlds, the feed would only see the reflector dish and would not see anything of the Earth behind, right? Satellite dish is pointing up, which basically means if you're sitting on the feed, you're looking down. And that is a bit of a problem, because there is nothing like a perfect feed. You can get a good feed, but not a perfect one. What is very good, I'm not saying perfect, but really very good, is the online microwave antenna book from W1GHZ, I always mix it up, Paul Wade. It's a real reference for everything compared in terms of everything with dealing with microwave antennas, and in particular with parabolic dishes. And there's a whole lot of information one could take out of this. And there are many plots and simulations and reasons and arguments. And the thing is that a typical feed beam illumination looks like this curve here, right? So you see, and the blue one is actually what you would like to have, right? You would like to have illumination just up to the edge and nothing outside of it. And this one is what you actually get. And you already see that there's some part which is actually looking to the sides of the antenna. And that's wasted in terms of transmitting, and it's collecting noise in terms of receiving. And there are some rules of thumb where you want to place this edge, basically. If you place it at the 10 dB down level, so basically peak of the feed, going to the outside, 10 dBs down, then you maximize for the gain, which may or may not be okay. What is sometimes even the better choice is you maximize for best signal over noise, because especially for the receiving part, that's what you're interested in. And then you should place this edge level on something like 13 to 16 dBs down. I'm perfectly aware that this is quite hard to measure, but then there's many good documents for this, and I'll come to this in a minute. I have been also asked what's the difference between a prime focus dish and an offset dish. And on the left-hand side, you see what many of us have been used in the past for Oscar 40 for the Mode S downlink. So this is the patch feed from James Miller G3RUH. And on the right-hand side, that's what you get basically from your local hardware dealer if you want to buy a TV satellite dish. So this is the offset, that's the prime focus. If we draw this now differently, then the prime focus is very easy to understand, because it's literally the focal point which you would expect if you have this kind of concave shape. So you place your feed horn there or whatever you need, and you're basically done. The problem is now, this is now the, let's say, perfect illuminated dish. But you have some parts going to this side, and also, let's say, sticking outside of the plane of this presentation. The feed is looking technically rather direction to Earth, like that, right? So the feed is looking down. So whatever is on the side, the feed will see quite a lot of the warm Earth. That's one problem. And the second problem is the feed, as you see here, is in the middle of the main direction of radiation. So there's something called feed blockage. part of the beam will be blocked by the feed itself, which also takes away a bit of efficiency. And these two issues are being worked around basically by using an offset dish. You have the focal point here. Actually, the offset dish, as you see it here, would continue like that to the other side. And then you have, again, a prime focus dish. Put it another way, if I chop off that part here of the dish of the left-hand side, it would be the very same radiation characteristics. But you also see that the illumination angle of such a feed for the offset dish is much narrower. But you get away with the, let's say, spillage on the sides of the dish, and there's no feed blockage anymore. So most of the times the offset dishes are more efficient. And there is a small, let's say, guiding chart. Any dish or any feed has some kind of opening angle. And of course, the higher the opening angle, the larger the opening angle, 180 degrees, for instance, here, the lower is the gain if you would take the feed as an antenna for itself. What I haven't explained yet is the x-axis here. It's called F/D. And it's basically a measure on the depth of the dish. You can have very deep dishes, which have sides which go up quite a lot. And you can have very shallow dishes, like most of the offset dishes, which are only like that. And low F/D, 0.25, 0.3 is a very deep dish. And a shallow dish has something like 0.7, 0.8 F/D. And you already see that your feed has to match basically this F/D parameter. That's the whole key point, actually. And not every feed works well with any F/D. So we have these very popular helix antennas. They work better if you have these offset dishes, because you have to focus the energy a bit better. So they work best somewhere in the order of 0.5 to 0.7, depending on how many turns you have. You have a cylindrical horn, or sometimes also called coffee can feed. They work better for deep dishes. What was also used quite some time was a patch antenna from K3TZ, Tim, I think was his name, also better used for deep dishes. And then there's something called the W2 IMU horn, which is also better for, let's say, shallow dishes. This one is quite exceptional because, we will see this later, it has a very clean diagram. So by design, it has no currents on the rim of the horn exit. Therefore, the amount of side lobes generated is very low, and it has a very clean beam shape. So coming to dual feeds, there has been an idea from Peter Gödecke DJ7GP in the AMSAT-DL journal, and but he wasn't actually able to properly simulate it and then machine it. But then some other guy, Johannes, came up, DC5G and he was able to simulate it, machine it, and I think he has sold a couple of those at the ham radio in Friedrichshafen. So, of course, the advantage is you have a dual feed. You only need one antenna, and this is kind of tailored for an F/D of 0.7, so that would fit very nicely to an offset dish. What is very important for these kind of setups is that you have a high isolation between the transmit and a receive path, because otherwise what happens if you flip the PTT switch, then your LNA would just go poof. But 60 dBs should be enough. So things like this do exist. As a short reminder, that's the transponder. As Peter already explained, the uplink will be right-hand circular polarization, and the downlink will be horizontally, vertically separated. So we need basically something twisty on the uplink and two on the downlink if we really want to use both. That is also, again, the table of the leaflet we have produced. One should take this last line with a pinch of salt, because these numbers are calculated in the case you actually want to use the whole 8 megahertz with one signal. So if you don't use 8 megahertz of bandwidth, but 4, then this number scales by the bandwidth. So it's only 50 watts. If you only want to use 1 megahertz because you have low resolution, or you don't want to have, let's say, you turn up the compression a bit more, then this number scales down accordingly. So the reason for the separation on the downlink was, one of the reasons was that we want to avoid the interference of the wideband transponder into the narrowband transponder. And this has something to do with these shoulders you have seen in the talk from Peter. If you have a bad power amplifier and you overdrive it, basically, you have intermodulation products, third order, which will basically generate these shoulders, left and right. And these shoulders would come into the narrowband transponder if we wouldn't have this separation vertically, horizontally, which give us another 20 dBs of isolation. And this node is basically a reference to this LNB, how is it called? Not tilt, but skew, LNB skew, right? That the local vertical might not be vertical, but it may be actually horizontal, especially if you're living in Rio or Penang. Okay, the rest I've explained. Polarization. We've spoken about feeds, and then there's polarization. Feeds and polarization are technically two different things, although most of the times they are combined in one element. And one possible example of combining this is this arrangement here. So that is one of these W2 IMU horns. So that's actually a flared horn with a cylindrical section in front of it, and a so-called septum transformer, invented, or let's say recalculated for amateur radio purposes by Stenek, I think is his name, OK1 DFC for EME purposes. So that's basically a sheet metal which some carefully calculated steps. And the thing is now that at the rear side, you have now two probes. One probe coming in from that side, and the other one coming in from the other side. And one will be left-hand circular, and one will be right-hand circular polarization. And for the EME people, this is perfect, because one is used for uplink, basically, for transmit, and the other one is for receive, and the polarization gets reflected at the moon. But you also see here on the left side, and that's a picture from Dave, G4HUP, that these kind of, let's say, stepped metal sheets are not very hard to machine. I mean, that's basically a bit of sawing and filing. And I really can recommend having a look on the EME community, because they have done this for a very, very long time, and they actually pretty much know how to do this by now. Okay, enough on the antennas. Up converters. I have presented this last year. This is kind of a, let's say, educational experience for myself. That was the 2 meters to 2.4 gigahertz up converter with something like 200, 250 milliwatts out. For those who don't want or cannot build this themselves, Michael Kuhn has a turnkey solution, or will have a turnkey solution. So this will be the phase 4 up converter. 144 to 2.4 gigahertz, 20 watt out, so sufficient. Standalone device, remotely controllable, and numerous protection circuits. We all know that we need them eventually. There's no price tag there yet. Unofficially, it's less than 400 euros. So I think it's perfectly reasonable. For the power amplifier, these things are available since quite some time now. Michael has something, obviously. That's probably the final stage of this up converter, solo. Then there's another ham radio operator in Germany who sells them as well. That's Roberto Zech, DG0VE.de. And I think we have his catalog in the AMSAT-UK shop as well. So have a look and get a copy. this output power is in the order of 90 to 100 watts. That's far too much for SSB, obviously, except for you want to use the, Drew, you mentioned the wet noodle. Maybe with a wet noodle you use this, but then it will be a boiled noodle very soon. But especially if you want to run a DATV transmitter and you cannot run it up to 100 watts because of the unlinearity. So you have to run it at maybe 5 to 10 watts. But this might be what you want to have. Yeah, well, I think I will manage. So this is what we have advertised for the last 1 or 2 years. They are still available on eBay. UMTS amplifiers for SSB, kind of usable. You have to, sometimes they're already retuned for 2.3 to 2.325, something like $100, 75 watts. If you don't drive them to their limit, they will be perfectly linear, easy to use, and yeah. And then, a couple of months ago, I fell over NXP and their suite of RF industrial, scientific, and medical devices. And okay, they claim a lot of things, and I have been talking to Kevin today and yesterday about it, and they remain to be proven, but still, there's only one way to do this, just try. And the applications, if you read them through, it's all sorts of things, and then amateur radio. So they go, what? Because you know how this works. You go to these RF transistors, and they're all modified, let's say, optimized for this UMTS band, 2140, and you have to kind of do some snowflaking and kind of somehow tweak them to 2.3, 2.4 gigahertz. But this one is genuinely optimized for 2.4. It's 250 watts saturated output, 14 dBs, and one big lump of copper. And I have the successor of this with me. I can pass it around if you promise. First of all, to give it back because I still have to test it, and second, please do not open the static bag. Yet again, we will have to test this and see how well it actually performs. Low noise block, also things which are available already. That's the LNA only, in the order of, let's say, 0.7 dBs. This one is a bit worse, 0.9 dBs, because it has an SMA connector that makes already difference. Then the converters, they have been on the market also since a couple of years, so no big surprises there. Again, Kuhn Electronic DB6NT, Roberto Zech DG0VE. Have a look in the AMSAT-UK office. Michael is coming with an all-in-one solution once more. The LNB. Please do not open the bag. I heard the click. Number 5 in the line, unbelievable. And the LNB will have an internal, basically modified LO, so it will convert the 10.4 down to 432 immediately. TCXO, no or negligible frequency drift, and mountable with a standard LNB peg. So I think that's what we all want. And just to show you how easy it is, Michael Fletcher, OH2 AUE, has already tried it with a standard stuff. So dish, 30 euros, modified LNB, something in the order of 20. You need a bit of power because the Fun Cube cannot supply 14 volts. But you can, let's say, supply it from the side. Maybe another 20. Fun Cube dongle is maybe a bit on the expensive side. It's very good, but a bit expensive. If you want to try it first with an RTL SDR stick, will be something around 20, and a laptop. And if you take this out of the equation, your whole receive equipment will be less than 100 euros, which is good enough for SSB and spectrum overview, and probably also educational purposes. And it has been demonstrated already that he has been able to receive Es'hail-1 telemetry, which is already in orbit with this setup from Finland. And you see this from Finland because, first of all, it has a lot of snow, and second, the offset antenna is awfully looking down to the horizon. Okay, conclusion. Last slide. Thank you, Jim. The microwave ground stations we are aiming for are a bit different than what we are used to up to now. But I think we can cope with that. We are radio amateurs. We're used to do things new, better, and different. I still think, compared to all linear transponders of the past, this might be the easiest ever. Because you get away with no Doppler, you don't need rotators, you have to set it up once, and yeah, except for the tree of the neighbor, which you have to cut off, this might be really easy. Again, a reminder, we have the leaflet with all the key information in the AMSAT UK shop. We have the catalog from Roberto there. Do we have the stuff from Michael Kuhne there as well?
Yes.
Go there, grab all the information you want, and if there's anything left, feel free to contact us. Thank you very much.
Thanks, Aki. Very interesting. He's brought exactly back on schedule. Should we just take a couple of questions, if there are any, for either for Peter or Akim? David.
Thanks to you both for a very interesting and illuminating presentation on something which we've been looking forward to for years. The nice people at Mitsubishi haven't put AGC in the transponder on the satellite, and normally they will be running their transponders with almost no signal coming up from the ground, except for the one they're looking for. Your uplink is co-shared with tens of thousands, possibly hundreds of thousands of Wi-Fi signals. How much sort of loss do you anticipate that's going to be on the uplink signal? How much compensation will operators need to make for that on the ground?
Okay. Actually, that was one of the first things we were quite worried about, because there will be literally millions of Wi-Fi access points radiating on this very frequency band. So we did some estimations about the number of access points, about the power the access points are using, radiation characteristics, and so on and so forth. And we actually found out that the dominating contribution still will be, as seen from the satellite, the warm Earth at 300 kelvins, and which is kind of a good thing. So, which doesn't mean that we are completely free of any ground-based interference. We have some minor worries about something called space fence from the US Navy, Air Force, something, and they are running at 2.3 gigahertz, 2.4, 2.5 maybe, with enormous peak pulse powers. And it's very similar to what we had with, I think it was PavePort on Oscar 40 on U-band at that time, 70 centimeter band. This is really hard to simulate, and I think we have to see what happens. On the other hand, I have to say, the designers from Melco and Es'hail-2 have a very good filter in front of the receiver, better than anything we had in the past. Obviously, we cannot show you the diagrams, and we have also only been given a very, very short, very brief diagram, but we were looking at it and say, well, this looks very impressive. So while I cannot say that we are completely safe from these kinds of interferences, currently we feel quite okay. But the rest, I think we have to see.
Okay, thank you. Any other questions? Okay. Any from the TV stream? Any questions from the TV stream? I'm getting a shake of the head. Okay. Both of you, thank you very much indeed. Very interesting, and going to be really interesting to see how that goes.